Yeah, so we're the magnetic haptics team. This first slide is just our poster. We're gonna skip by this for now, but we'll come back at the end if there are any questions. This has most of the important information on it, but we're gonna go into a little more detail into each of the sections. So just to give a little bit of background on our project, a haptic device is any device that provides touch or force feedback to a user. So examples range from like rumble seats in theaters all the way to more complex devices like this one shown in the top right that lets a user interact with a virtual environment and then uses motors and linkages to provide force feedback and let the user kind of feel forces as they're exploring this virtual environment. So the problem with devices like this one in the top are that since they use motors and mechanical linkages, they're not responsive or sensitive enough for really delicate applications like eye surgery. So the objective of our project was to design an untethered haptic device that uses electromagnets to apply forces and feedback rather than mechanical motors and linkages. And this will allow for really delicate operations and forces like you would see in something like an eye surgery. So in the lower picture on the right, this gives kind of a general idea of what this device is going to be doing. So the user will be able to hold a stylus that's totally disconnected from any device and just has a magnet in the tip. And they'll be able to move this stylus around inside a small work volume, so this area in the middle, and then an array of electromagnets will apply forces upon that stylus. And while they're doing this, the user is going to be looking at a separate computer monitor or screen and be able to see a virtual environment. So the idea is that this could be used for eye surgery training or something similar to that. So just to go a very broad overview of our project, this picture on the right is the current design, kind of where we're at with the full system. And because this is a complex, large project and we're a large team, it's been broken up into several different subsystems and several sub-teams. And that's kind of the way we're going to go through this presentation. So first is the design team, and the design team, we had to design a camera and lighting system to track the user's stylus in 3D, as well as designing the user workspace that they'll be working in. Second is going to be the structure team, and they designed tooling and manufactured the electromagnets, as well as designed and built the overall frame for this device. And last is going to be the cooling team. And just like it sounds, they had to design a cooling system to prevent the electromagnets from overheating because they generate a lot of heat. So we'll jump right into the design team. And the first component we're going to talk about that's really critical to our design is what we call the Wasp nest. And this Wasp nest basically is this cast part made out of ceramic that serves two purposes. First is that it locates and holds the 8 electromagnets. You can see that in this picture on the right, that there are these 8 electromagnets. This is an exploded view. And then this center white piece is the Wasp nest, and it has 8 pockets that the electromagnets will sit in, and it will securely hold them in the needed orientation. The second purpose of the Wasp nest is to define the user workspace. So this is the actual space where the user's hand is going to sit and where they're going to put their stylus and move it around. And that is this center area right here where my cursor is. It's a roughly spherical volume of about 7 centimeters in diameter, which is about the size of a tennis ball. So it's not very big just because of the limited distance for the electromagnets. But since we're planning to use this for something like eye surgery training, you don't really need a big space. So we figured that about that size would be sufficient. And this image on the right, we went through several prototypes, several different iterations, or sorry, this image on the left shows the most recent prototype iteration that we went through. And this one is cast out of concrete. The final one will be made out of a highly conductive ceramic material to help with cooling. And the cooling team will talk about that later. For now, Ethan's going to take over and talk about the camera system for the device.
Thanks, Jake. These cameras are the only two of their kind in the world. They're special made to achieve high frame rates as well as high resolution that would be useful in our project. These cameras act as our main and only sensor in the project. These cameras point towards the stylist in the work area and track it in three-dimensional space. These cameras tell the computer where the stylist is and then send that signal from the computer to the electromagnetics amplifier in order to provide force on the stylus so the user can feel that. As a means to create space for the user to be able to work in that space, we moved the cameras to the rear, as you can see. And so we redirected that camera with these mirrors shown here. We chose special mirrors that had the reflectant material on the outer surface to prevent light refraction that would confuse the computer program. Apart from these special mirrors, we also implemented an extremely high bright light that would show on a black work surface so that the camera would see the stylist and be able to repeat this regardless of the ambient light conditions in the room. So Andreas is going to tell us a little bit more about how these electromagnets are built and constructed.
Thanks. So like Jacob mentioned at the beginning, the structure team focused on the electromagnet fabrication and the frame fabrication. So for the electromagnets, we were asked to present on what we did before and after spring break. Before spring break, we were actually able to fabricate 4 different iterations of the electromagnets. And the closest one to the final design is shown on the left here. The final electromagnet is made from a square wire. It's 21 gauge bondable copper wire. After spring break, we focused on, since we couldn't fabricate more by going into the lab, we focused on making more visually appealing models and exploded views. The image on the right here shows a cross-sectional view, so it's cut in half of the actual model, a cross-sectional view of the components that were used to fabricate the electromagnet. So the pinkish copper color in the middle represents the electromagnet, and the rest of the components are what was used to create the inside shape and the outside shape of the magnet. So the following video here we have shows the fabrication process of winding the electromagnets. So first we have these steel gray pieces. Those create the inner shape of the magnet. And once that is assembled, we start winding the magnet simultaneously while putting these black caps over the top to give the outer shape of the magnet. So we're going to play that again just to give you an idea. And the reason we have 2 of the inner shapes, the inner contour shapes, is so that once the whole process is done, you pull the rod that's holding everything together, you pull that out, and you can actually collapse the 2 inside pieces and pull them out without scratching the wire, which we were trying to avoid to prevent damage. Next we'll hear from Spencer, who will explain more about the extruded aluminum frame.
Great, thanks, Andres. So the first part of the frame that the structure team is handling, we affectionately call the cradle. And so what it does is it is basically exactly what it sounds like. It's a cradle for the wasp nest that holds it in place and mounts it to the overall frame of the larger frame of the device. So again, we were asked to speak to what we did before spring break and what we've done since spring break. So before spring break, we had assembled the cradle, as you can see on the picture on the left, as it houses one of the wasp nest prototypes as well. So this was our 3rd iteration of the cradle. And we had just decided to put those little rubber pieces you can see at the bottom in kind of a pinkish color. We had just put those in there and assembled it And then spring break happened, and with the COVID pandemic, we were unable to move further with that. But what we did do after spring break was we enhanced the CAD models that we were using, as you can see on the right. So we made this CAD model, and we also decided to go with a thinner pad that goes all the way around there. So all of those pads you can see, we chose it to be thinner so that it would better house and provide a more snug fit for the wasp nest. We also added fasteners and exploded views for all of our CAD models. And then now I'll talk a little bit about the overall structure to which it mounts. So this is what the overall structure looks like. It's kind of a stripped down model, but this is what the frame looks like. So before spring break, we had assembled the basic frame and then mounted some of the amplifiers and power sources to the actual frame. You can see that on the left. But one thing that you may notice is up towards the top left where the cursor is right now, it looks like that bar is kind of tilted and out of whack, which it is. So after we had assembled this, we realized that that side of the frame was tilted, which could cause problems for the cameras and create an uneven workspace. So what we did after spring break, as you can see here where the cursor is, we added this guide piece to the other side as well. So now this guide piece exists on both sides of it, and it holds the frame completely flat and level. And then the other thing we also did was enhancing all of our CAD models, adding fasteners, and we finished up the design of this actual thing. We added a door to the side. I removed it so you could see the lock guide that I was just referring to, but we also added doors and panels to the outside to make it completely enclosed, as you can see on these white pieces. And that's for the structure team. And now we'll hear from Calvin for the cooling team.
All right, so here on the right, you guys are going to see the full assembly of, or our full cooling assembly design. And you'll see the wasp nest up above that uses the ceramic material. So a common issue with electromagnetic systems is heat management. Electromagnets get really hot and need to be cooled down so that they can be used continuously. So the main goal of the cooling team was to maximize the amount of time that these electromagnets can run before overheating. And so obviously the longer that they can run before overheating, the longer the user can engage in the haptic experience. So now for some of our other goals. One of the main other goals was maximizing the electromagnetic force potential that the electromagnets can generate. Now, this may not seem like a cooling problem, but it is because the amount of space added between the workspace, which is where the user puts their stylus, and the electromagnets significantly decreases the forces that can be rendered by the electromagnets on the stylus. So this means that our cooling design needed to minimize the space between the electromagnets and this workspace. And so additional goals include not short-circuiting the electromagnetic coils and integrating the cooling design with the structural design. Obviously, we ran into some issues with the COVID-19 pandemic. And so before spring break, we did many iterations on the ceramic casting method to be able to manufacture both the wasp nest and these ceramic inserts which go inside of the electromagnetic coils. And we also researched various cooling components and methods. And after spring break, we were able to produce COMSOL models, which are heating models and cooling models to determine the optimal design. And we were also able to create assemblies, computer models of these of the cooling assemblies. Now we'll hear from Andres for more about cooling.
Thank you, Calvin. So for our coil subassembly, before spring break, we worked on the actual design that you can see on the left. So the electromagnet, which is used to generate the force for the user also generates a lot of heat. So we have a thermal paste that goes in between that and the wasp nest, which allows for an interface of heat transfer. We have a ceramic material insert, which fits inside of the electromagnetic coil, a heat pipe, which we then use to draw heat from the material out towards a heat sink, which then uses natural convection to ultimately cool the system. So the ceramic insert, because of the coil was such a specific shape, we had to go through multiple iterations of trying different 3D prints and different ways of removing the mold, different mold releases and stuff. And this led us to our final iteration on the bottom, which we had the most success in actually removing a ceramic insert. So this leads us into our post-spring break. So after spring break, we spent most of our time actually performing modeling and simulating results. So we approached this problem from a kind of ground up perspective, and we started with 8 of our coils that were suspended in air in place of where they would actually fit inside the wasp nest. And then from this, all under the same constraints of running for 500 minutes with all coils running 150 watts, we began to add different of our cooling products until we got to our final design, which featured a ceramic nest, the ceramic insert with all the heat pipes. And judging off of just the max safe surface temperature that's required by ASTM, we actually were well under our goal of being below 60 degrees Celsius, as you can see from the blue. So Calvin, if you'd like to finish off.
All right. So we can see here is just a brief summary of our goals and the results we achieved. We were able to achieve our main goal of being able to run for at least 20 minutes before overheating. We actually never overheated in the simulations, but the simulations only run for 500 minutes. So we were able to achieve that goal along with the safe surface temperature goal, which Andreas mentioned earlier. We were also able to not have to increase the distance between the coils and the workspace at all, because our unique cooling design allowed for that space to be minimal. If we had used a traditional air cooling method, we would have had to increase that space and decrease the electromagnetic forces that could be rendered. We were also able to achieve the goal of not short-circuiting electromagnets by using an electrically insulative yet thermally conductive material, which was that ceramic material that we're using on the wasp nest. And the cooling design was also very well integrated with the structural design, because the ceramic wasp nest supports all the electromagnets in the locations they need to be while providing a cooling medium. And one more thing that we should mention is this cooling method is not seen in other cooling devices, so it is a very unique and you could say groundbreaking cooling method for cooling electromagnets. Although the COVID-19 pandemic hampered our ability to fully manufacture this cooling assembly, we do feel that we were able to achieve our goals in designing a cooling system that we can accurately predict the performance of using computer models. We would like to give a special thanks to our advisor, Dr. Jake Abbott, and the graduate student who helped guide us along this process, Ashkan Porkan, for their help and guidance to help us become better engineers and learn about the engineering process. So now we'd like to take any questions from you guys.